Okay, for this video, I'll be going through Pure Physics Dynamics 2 Tutorial 3. Yeah. Okay, so the first question is actually about drawing your vector diagram. So the vector diagram in this chapter is a little bit different from the vector diagram that you have done in your scalar and vector, which is in your chapter 1. Okay, for this chapter, it focuses mainly on a system whereby there is no resultant force. Okay, there's no F net, there's no resultant force. So when there's no resultant force, the object is either moving with constant velocity or not moving. Okay, so most of the time it is under the case of not moving, whereby you'll see the object is being balanced, okay, or they will say in equilibrium. Okay, so it's very different from the first chapter's vector diagram, whereby there will be resultant force. Okay, so there will be a double arrow. Okay, we'll still be seeing the double arrow here, but it will be a little bit different from what you have seen in chapter 1. Okay, so in figure 1.1, a microphone with a weight of 5 Newton, okay, hangs by its wire from the ceiling. A string is attached horizontally to the end of the microphone, so this is the string, okay, exerting a force of 2 Newton. And figure 1.2 shows the 3 forces acting on the microphone. So there is a wire, okay, and the weight is definitely pointing downwards, vertically downwards, so we have it here. Then we have force F, which is 2 Newton, and also there will be a tension force acting on the microphone. So you don't need to draw the whole microphone, you just need to start off with either a cross or a dot. Okay, so in this case, they want us to determine the magnitude and direction of the resultant force due to the weight and the force of the string. So they are asking us to draw the resultant force for W and F. So if I were to do it very quickly, so this is W. Of course, you need to draw it to scale, but now I'm just doing as a sketch. Okay, so the skills that you learn in chapter 1 is still applicable, whereby you have to either draw it in a parallelogram method or triangle method. And actually it is by arranging them in tip to tail. So currently their orientation is tail to tail. Okay, so you actually need to shift it such that they are arranged to tip to tail. So I can either shift my W here, okay, or I shift my F here. Okay, keeping in mind that I am making sure that the magnitude and the direction after I shift remains the same. Okay, so this looks like a parallelogram, and this is the start point and this is the end point, so the resultant will be this. So this is where you will draw your resultant force with your double arrow. Okay, but if you are using the triangle method, okay, so it's still shifting it into tip to tail, so you will draw your W over here and then you will erase the original. Okay, but bearing in mind that the W have to be shifted such that it is as the original direction and have the same magnitude. Then now you have your start and your end, so you go from your start to your end. It is this resultant force here. So this is actually the answer, the resultant force due to the weight and force of the string. So it is always about putting them in tip to tail. So now you can actually measure the length of this double arrow, and that will be the magnitude, and then the direction will be using F as a reference. Okay, so this is the answer. Okay, so this is by the parallelogram method, something like what I have drawn above, and this is by the tip to tail method or the triangle method. So you get 22 degrees from weight. So please try it out. Now state the magnitude and direction of the tension in the wire. Okay, so this is where the key concept lies. So if I have these 3 forces, right, T, F, and W. Okay, so if I were to arrange them in tip to tail, it will look like F, W, and T. it will form a closed loop triangle, right? It will form a closed loop triangle. Of course, the direction and the magnitude of all these three must be the same. So if I were to draw this, it is very different from, let's say I have this and this, okay? So this is where we have a resultant force, okay? It's still a triangle method, but I'm just showing my F and my W, okay? My T is not anywhere here, okay? So it looks exactly like this triangle that I've drawn. So what does it say? It means that the resultant force of F and W is equal and opposite to T. Okay, so basically the resultant force of F and W is this. It is now balanced by your T because they are in opposite direction and having the same magnitude. Okay, similarly I can say that the resultant force of F and T again is equal and opposite to W. Okay, so if I were to draw the resultant force of T and F, okay, so it will be this. Okay, you find that this is actually equal and opposite to the force of W. Equal and opposite to the force of W. So that is how they can balance to achieve a no resultant force system. Okay, and this is important for this chapter. You need to understand this concept. So I can do the third one, the resultant force of before I write, can you predict? Because I already talked about resultant force of F and W. I've talked about the resultant force of F and T. So the last one will be the resultant force of T and W is equal and opposite to F. So I will now attempt to draw the resultant force of T and W. So T is this way, W is this way. Okay, so this is the resultant force of T and W. Okay, you find that it is equal and opposite to the force F. Okay, so this brings us to the case of no resultant force, and that is why this microphone can stay in this position. Okay, so if you understand this, then they want us to state the magnitude and direction of the tension in the wire T. So because it is equal and opposite is for the direction, equal is for the magnitude, right? Because now we are dealing with vectors, we need magnitude and direction. So the magnitude should be equal. The direction will be 180 degrees from the original. It is opposite to it, so that's why it's 158 degrees. Okay, so we then apply all this to question 2. So of course you start with a scale, right? That was covered in the first time when we do vector diagram. Okay, and they say for the question, it is held in a horizontal position. Okay, held in horizontal position, that means it is not moving. Okay, it is in equilibrium. So meaning it will have no resultant force. So when you're drawing these three forces, there will be no resultant force. Okay, so you can so I prefer to use the tip to tail triangle method, but before you do that, maybe you can do a sketch. So let the cross be the rod. Okay, because all the three forces are acting on the rod. So we have this T due to the wire, and it is about 50 degrees. Okay, then you have your W, which is vertically down, and you have the force of hinge on rod, and we are supposed to find the force acting on the hinge. Okay, so it is acting on the rod. So now T and W, they are actually two forces, and I can actually draw my W this way, I arrange it in tip to tail, so I know the direction of the hinge on the rod is going to be in this direction. Okay, but they want the direction of the force acting on the hinge. So this is where you need to apply your third law, right? The hinge exerts a force on the rod. Let's say I call this force H, right? That means, sorry, this is the resultant force of T and W, right? T and W. Okay, so that means the force that the hinge exerts on the rod, right, must be equal and opposite to the resultant force of T and W. So I'll call it H. Okay, but they now want the direction of the force acting on the hinge. Okay, so anyway, let's draw the tip to tail. Now we roughly know what is the direction. Okay, so this is T, which is 8 newtons, and it is 50 degrees to the horizontal. I arrange my W, which is 12 newton, in vertically downwards, and therefore the force at the hinge will be this closed loop triangle. Okay, so if you draw it out, you will see that this must be a closed loop triangle. Right, so if I were just to draw T, right, then this is my W, these two forces. So this is the resultant force of F net of T and W. So the third force must be equal and opposite to the F net of T and W, so as to balance it, to bring us to a case of no resultant force. Okay, so you can try it out and check your answer. So third question, more practices for you. So this one is a little bit tougher because you don't know the value of T2 and T1, but you do know that the weight is 12 Newton. Okay, so I'm going to write something here. Resultant force F net of T1 and T2 is equal and opposite to 12 Newton. That means if my 12 Newton is this way, right? Okay, having a certain length and vertically downwards. So the F net of T1 and T2 must be this way, in the opposite direction and having the same length. So even though you do not know the length of T2 and T1, you already know what is their resultant force. It is this 12 Newton, but it is facing upwards. So you know the direction of T1 with respect to the vertical, right? So this is 90 minus 65, so we have 25 degrees. This is 90 minus 35, we have 55 degrees. Okay, so we can draw T1 and T2 in this direction first, but we don't know the magnitude. But their resultant force will be equals to this 12 Newton. So if I were to shift T1, I need to shift it in a way such that it is parallel to the original T1. I need to shift it, right? And when I shift my ruler, it ends over here. This will tell me that this is the T1, the real value of T1. Okay, because if I were to shift T1 to here, it will not fulfill the condition of having a 12 Newton resultant force. Okay, so make sure you shift your ruler such that it is parallel to T1, or if you want, you can also shift T2. Okay, you shift it in this way. So if I were to shift T2 here, I keep the direction the same. Okay, but you see, if I were to stop here, it falls short of the condition that the resultant force must be 12 Newton. And if I shift T2 here, okay, same direction, but it doesn't even meet the requirement that the resultant force needs to be 12 Newton. So I need to shift it in such a way that, you know, it actually meets this 12 Newton and at the same time it keeps to the same direction. So if you don't know how to shift it to get parallel lines, you can look for me, right? I can teach you how to shift it. It's easier to show you physically, but you need to understand this and the part whereby the resultant force of T1 and T2 is equal to 12 Newton. That means I can write the other two statements. F net of T1 and 12 Newton is equal and opposite to T2. The third statement will be F net of T2 and 12 Newton is equal and opposite to T1. Okay, so these are the three conditions because I have three forces. So they actually sort of counteract one another. Okay, so check your answer. You should get 10 Newton and 5.2. And then question 4 also similar. The answers have been uploaded on Google Classroom. Okay, maybe do question 5 now. Okay, so question 5, a spacecraft descends vertically towards the surface of the moon with a constant speed of 2 meters per second. So this is the initial speed. The spacecraft and the crew have a total mass of 15,000 kg. Please assign the letters, which is m, and the g on Earth is 1.6 Newton per kg. Okay, read on. During its descent, the upward force produced by its rocket thrust is 24,000 Newton. So this is the rocket. I have a 24,000 Newton acting upwards, right? But I also have the weight. Okay, I know the weight is actually mg, right? W equals mg. So the mass is 15000 multiplied by 1.6. I get 24000 Newton. So as you can see, there are two forces acting on this spacecraft. One is the upward force by the rocket thruster. The other one is the weight, which is due to the pull of moon on this rocket, on this spacecraft. Okay, and you find that they are equal in magnitude but opposite in direction. Therefore, F net is 0. If F net equals to 0, that means acceleration is 0 because F net equals ma. Right? Since acceleration is 0, there are two conditions. Either it will be stationary or it will be moving with constant velocity. Okay, but since it was already moving, therefore it will move with constant velocity. So this is shown. Okay, so you need to explain in terms of the forces and most importantly F net. So this F net is a very important concept that you need to apply in dynamics too. Okay, in the final 18 seconds of the descent, so this will be my T, the upward force is increased such that the spacecraft decelerates at 0.10. So whenever there's acceleration or deceleration, there will now be F net. Okay, so they want us to calculate the new upward force. So let's calculate the new F net. F net equals to ma. Okay, they give us the A of 0.1. The mass is still 15000 times 0.1. So the F net is 1500 Newton. And they tell us that the upward force is increased. That means this extra F net, this extra 1500 Newton is added on to the original 24,000 Newton plus 1500, right? And the weight remains the same, right? There should be no reason why the weight changes. Therefore, with this upward force, right, then there will be an acceleration of 0.10. Okay, so the force thrust or upward force is now 25,500. Okay, they want us to calculate the speed just before it touches down. So a lot of students will be tempted to write 0 because that is what they see. After it touches, the speed is 0. But that is not true, right? It has a certain speed. It's only after some time, once it makes contact with the ground, then the speed will become 0. Okay? So we need to calculate the velocity, right, before it touches down. And since it was decelerating, we actually had our initial speed, so we should use our A equals to V minus U over T. Okay, so this formula actually came about in when we were doing kinematics, and I think I mentioned before that the connecting concept is the acceleration, because in kinematics you talk about acceleration. In dynamics too, you have your F net equals ma. Both have the same acceleration, so they can be lumped together. So we actually have the acceleration, okay, is 0.10. Okay, or if you want, you can put it as negative. Now, the v is actually the final speed, which we don't know. The u is the initial speed, I think is 2. Okay, and t is final 18, right? So you will get minus 1.8 equals to v minus 2. So v will then be equals to 2 minus 1.8. So it's 0.20 meter per second. Okay. So in this case, I actually let the acceleration becomes negative. Okay. So that's why I get a value of 0.2. But in this solution, they take upwards as positive, so they just do it this way. Okay, so they want us to calculate the height of the spacecraft at the moment when the upward force is increased. Okay, how high was it before it touches the ground? Okay, so don't forget, initially it was at a certain speed of minus 2 or 2, right? Then it started to apply an upward force. So in the end, the final speed is 0.2 or minus 0.2. Okay, and because they are finding the height, which is the distance, so you can make use of your VT graph. Now, VT graph is actually a very useful tool. Okay, you must learn to use this. So you are actually calculating the trapezium and not just the triangle. Okay, the trapezium. So you'll get answer of 19.8. Okay, question 6, a very popular question for us to practice the explanation part. Okay, so a skydiver jumps off a plane in free fall. Free fall meaning no air resistance. Okay, and he is actually accelerating. Okay, and he falls vertically downwards. So figure 6.2 shows the velocity time graph. Okay, so determine the initial acceleration just before he jumps off the plane. So initially air resistance is 0 because free fall. Okay, so the only force acting on him is the gravitational force. So F net equals to ma. So since your g of Earth given is 10, okay, we use this convenient value. Okay, so the acceleration will be 10 meter per second square. So it will have to be a constant gradient of 10. Okay, now calculate the displacement which the diver has fallen for the first 3 seconds, assuming that air resistance is negligible. Okay, so for the first 3 seconds, right, the final speed that he reached after first 3 seconds is 30. How do I get that? A equals to V minus U over T. So assuming he jumped off the plane, his initial velocity is 0. This is what we want to find. Acceleration is 10 and T will be 3 seconds. So we get 30 meter per second. Okay, so a very common mistake here is students will take 30 multiplied by 3, okay, to get 90. In fact, this is not correct because the students forget that the 30 meter per second was his final speed after 3 seconds. But before that, it was increasing at a constant rate, right? So therefore, we should always draw your VT graph and then get the area under the graph for VT graph to represent the displacement or distance. Now, using ideas about forces, when you see this, you must mention your forces. And because it's dynamics, you must talk about F net. Explain why the acceleration of the skydiver decreases from A to B. So let's take a look. From A to B, we are looking at the velocity time graph. The gradient represents acceleration. Okay, so for the first part, it is constant gradient. Therefore, we have constant acceleration. But as it goes from A to B, you see that the gradient actually decreases. The gradient decreases, right? So it went from steep to gentle, steep to gentle. So the gradient actually decreases, which means the acceleration decreases. So this means that the velocity, very important, is increasing at a decreasing rate. the increase in velocity is not that much. Okay, it's not that much already, but it is still increasing. This is important. Whenever student sees decreasing acceleration, right? This is a very common mistake. Whenever students see decreasing acceleration, they will say that the object is slowing down. This is not true. Whenever we see acceleration, the velocity or the speed is still increasing, the object is still speeding up, but it is speeding up at a decreasing rate. Okay, so take note of this. If you forgot, go and revise on your kinematics. So why the acceleration decreases from A to B? Because when he's falling, initially there's no air resistance, but as he falls and his velocity increases, right, and he reaches nearer to the ground, there will be more air, and hence there will be more air resistance. So this statement is very important. Air resistance increase with increasing velocity. What other factors will also increase air resistance? Air resistance changes or increases when velocity of the moving object increases, or if the surface area or area in contact with air increases. And the last one, less common, is when the density of air increases. Okay, so these three effects will lead to an increase in air resistance, and of course the other way is true lah. So as the resultant force is equal to weight minus air resistance, the resultant force decreases, right? Your F net equals to your W minus air resistance. So you can draw a free body diagram. Initially W is like that, but as you keep on increasing in speed, your air resistance will increase, and therefore your F net will get lesser and lesser. So what happens when F net gets lesser and lesser, right? The acceleration will decrease as resultant force decrease, because F net equals ma. So we are using a lot of F net over here because the F net will tell us how the forces are interacting with one another. Okay, then why the skydiver falls with constant velocity after B? When we see constant velocity, we know that the acceleration is 0, and therefore the F net is 0. Okay, so what resulted in the F net becoming 0? Okay, so you see, as from A to B, the skydiver is having a decreasing acceleration, which means the velocity is still increasing, and as a result, the velocity increase will bring about air resistance to increase. So the air resistance will keep increasing until it is equal and opposite to the weight. So if I were to draw a free body diagram, W, just now I drew my air resistance arrow very small, but now the air resistance keep on increasing because the velocity keeps on increasing. So it increases until it is equal to weight, and that will lead to your F net to become 0. Your resultant force becomes 0. Okay, so if it becomes 0, then there will be two cases. The object will either stop moving, okay, remain stationary, or move with constant velocity. But since the object was already moving, it will then move with constant velocity, and this is what we call terminal velocity. Okay, so there's a difference between free fall. Free fall is falling without air resistance. The velocity will keep increasing. Terminal velocity is the constant maximum velocity. Okay, then what happens to the motion of the skydiver if he opens the parachute? When he opens up the parachute, the surface area increases, right? So the surface area in contact with air will increase, and that will result in increase in air resistance. So now I will draw my free body diagram. Just now it was like this, right? Equal and opposite, and now he suddenly opens up his parachute. So the air resistance is now so much greater than your weight. And what will happen to will there be F net? Yes, there will be, and it will be in the opposite direction of his motion. Okay, so when he opens the parachute, the air resistance becomes greater than the weight. The resultant force is now equals to weight minus air resistance, and the resultant force becomes upwards. So this is shown in my free body diagram. And therefore, if there is a resultant force opposite in direction to his motion, he will decelerate, right? Because now there's F net. If there's F net, there is acceleration. But because it is opposite to his motion, he will decelerate. Okay? Okay, question 7. A feather and a stone are released simultaneously from the same height. So given that the acceleration of free fall is the same, that means the G, or the acceleration due to gravitational force, is the same. Explain why the feather hits the ground much later than the stone. Now, as the feather has a smaller weight than the stone, correct? A smaller air resistance is required to balance its weight. Because as they both fall, they experience air resistance. But because the feather has a smaller weight compared to a rock, so the W is like that. So the W for the feather is lesser. So the feather actually needs lesser air resistance to balance its weight, which then leads to F net to be 0. And if F net is equals to 0, then we can say that it is no acceleration, and therefore it will move with constant velocity. So while the feather has its weight being balanced by the air resistance, and if we apply the same amount of air resistance, because they both fall they were both released at the same time, right? So you see that the air resistance experienced by the stone is still lesser than the W, meaning that there will be a F net. There will be a resultant force downwards. And whenever there's F net, there will be acceleration. So the rock will still, or the stone will still accelerate. Okay, so while the feather is already traveling with constant velocity, a low one, the speed of the stone is still increasing. Its velocity is still increasing. And after some time, because as speed increases, air resistance increases, so I can increase the air resistance. But as you can see, the length of the arrow is still shorter than the weight, correct? So there will still be acceleration. So the story repeats until in the end, possibly if they are dropped from a high height, then the air resistance will increase until it is equal and opposite to the weight. And then at that time, the stone will then be traveling with constant velocity, right? Because at that moment, right, the F net is 0. So acceleration is 0, so he'll move with constant velocity. So can you see that while the feather is having constant velocity right at the start, because its weight is easily balanced off by the air resistance, the stone is still taking its time to increase its velocity. So definitely the stone will hit the ground at a faster speed. So this is the explanation. As the feather has a smaller weight, a smaller air resistance is required to balance its weight. Hence, as the feather accelerates downwards, air resistance increases and balances the feather's weight earlier than that of the stone. So that was mentioned when I was talking about here, right? Since the feather reaches terminal velocity earlier and remains at terminal velocity, okay, while the stone continues to accelerate to a higher velocity, so in the end the stone will reach the ground more quickly than the feather. Okay, so take note, do not use the surface area here to justify your answer, because you wouldn't know whether I can have a feather that is like that, small surface area. I can have a stone that is like that. Okay, so we don't know whether the surface area is larger, but we should know that the stone will have a greater weight lah. There shouldn't be a stone with a weight that is less than a feather. Okay, so in the end, that's all for this tutorial.